Now we're going to try and calculate the pH of some weak acids and bases. This is going to be equilibrium, so we're going to use the ice method as we did back in equilibrium. So first of all, let's look at an equilibrium in which you have an acid or a base. And usually if you have an equilibrium, it means you have a weak acid and a weak base. Because if you have a strong one, it will dissociate completely. Okay, but in case of weak acids and bases, you get an equilibrium where the acid and the base are reversible. Okay, so which means that the reaction is going forward as well as backward. An example of this is acetic acid, which will dissociate in water to give hydronium ion as well as the acetate ion. But the acetic acid does not dissociate completely. So there is an equilibrium there. And so you can calculate Kc, which is the equilibrium constant for acetic acid, which is given by this. And here you have the hydronium ion and the acetate ion concentration divided by the concentration of the acetic acid. You will note that we don't use water in this because water is a liquid. Okay, again, liquids and solids are not part of the equilibrium or the Ka equilibrium constant calculation. So this is how you would calculate Ka, and this is called Ka because this is the equilibrium constant for an acid. If it was general equilibrium constant, you call it Kc as we did before, but in case of acid, we'll call this Ka. So it makes it a little bit easier for us to follow what equilibrium constant we are dealing with. So when you have hydronium ion concentration over here on the top, it means that if you have more concentration of hydronium ion, then you have a higher Ka, which means that you have a stronger acid, because remember that the more hydronium ion concentration you have, the higher pH, the higher or the lower pH you're going to have. Okay, and so that is directly related to the strength of the acid. Here are some Kas for the weak acids, and you don't have to know the name for all of these. Some of them you already know. Okay, for example, you already know hydrocyanic acid, hydrofluoric acid, hydrogen sulfate ion. You can see that over here now. The sulfuric acid itself, the first ionization was complete, but the second ionization is not complete. And so that's going to be in equilibrium over here. Acetic acid is by far the most common one that we're going to use, but you might see some other familiar ones. Again, don't memorize any of this because I'll give you all these constants. So a quick check, for example, for Ka of acid. So if you're given an acid and you're given the Kas and you're asked to figure out which one has the highest pH and which one has the lowest pH, then you're really looking at the concentrations over here. And remember, Ka, primarily the concentration you're looking at over here is for the hydronium ion concentration, because that was on the top of the formula. So you're looking for something that has high concentration, which means a lower negative number. Higher negative number means that you have a low concentration. So HF then becomes the highest for the pH, and HCN becomes the lowest. And again, the highest pH here has to do with acidity. Highest acidity, lowest acidity. High pH does not mean that you have a higher number. Higher pH here indicates acidity. So the calculations regarding Ka, they will be the same as you did before with the equilibrium constants. So if you're given the Ka value and the concentration of acids, you can calculate the concentration of all the ions at the equilibrium, and of course then the pH of the acid. So if the ionization is not complete, you're going to have a little bit of everything remaining in there during the change, okay, during the progress of the reaction, which means that you will have an equilibrium and you will have all the three ions present, unlike if you have complete dissociation going on. So then you can calculate for X, just like we did for equilibriums before, using the ICE method, initial, change, and then equilibrium. So the initial concentration will be given to you, for example, for the acid, and the initial concentration for hydronium, and whatever the conjugate base is going to be 0. The change is going to be when the acid dissociates and the hydronium ion starts appearing along with the conjugate base, and of course this will be equal depending on the mole ratio over here. If there are two of these, then you will have two of the X here also, and then equilibrium concentrations will be whatever is remaining from the change. Okay, so then you use those concentrations to carry out your calculations for the pH. One thing to keep in mind, and this is a lot more important in Ka than it was back in Kc, and it was a little bit important in Kc also. We addressed it a little bit, but here it becomes a little bit more important. Otherwise, you'll be doing so many calculations. Is about this minus x over here. Okay, and the minus x over here can really change your calculations because you can decide whether to use the quadratic equation or not in order to calculate the value of x. So how do you figure out if you have to use the x over here or not? Here you have to use the x because at some point you have to have an x in an algebraic equation. But the minus x, do you have to have this? Because it really increases your calculation. You have to use the quadratic equation if you use this minus x, especially if you can't square root everything. So the way to figure that out is if you have to use this or not is to see if the percent ionization is less than 5%. So if the percent ionization, that is the value of x, is less than 5% or equal to 5%, you can ignore x. As we do these calculations, I'm going to show you how to figure this out because this is important. Otherwise, you will be again lost in calculations. All right. So it's much better to ignore x if possible. Okay, so in some cases, in fact, in most cases, you can ignore x. Okay, in some cases you can't, but in most cases you can. Again, so if the percent ionization is less or equal or less than 5%, you can ignore x. So let's look at an example of calculating the pH of a weak acid. Calculate the pH of a 0.18 molar solution of a weak acid that has Ka of 9.2 times 10 to the negative 6. So here is our equation. Again, it's a random acid, so it doesn't matter. It doesn't give you any specific acid. So we're going to go ahead and assume that it is H plus and A minus, okay, just a 1-to-1 mole ratio and all that good stuff. So the initial concentration is given to us at 0.18 molar. That's what's given to us. We don't know the concentrations of of hydronium ion and the conjugate base. So that's 0, 0 in the beginning, and then the change is then of course plus x, and then minus x for the acid. And then at equilibrium, you will have 0.18 minus x for the acid, and then x and x for the acid and the conjugate base. So what we're going to do is set up our equilibrium equation over here. So this is the Ka, and then of course the hydronium ion, the conjugate base is here, and then the acid is at the bottom. So this is the minus x over here. So what we're going to do right now is we're going to go ahead and ignore the minus x for the concentration for now. Okay, so we'll go ahead and ignore that, which means that this is our equation then, where you have 9.2 times 10 to the negative 6 is equal to x squared divided by 0.18 molar. So this becomes a lot easier to work with. So once you have x, then you then figure out if you really needed to calculate x. Okay, and remember I said to you before, this is what you look for. Okay, and that's the percent ionization, which means you take the value of the x that you have calculated divided by the initial concentration, which is 0.18, and then find out the percent of that. And so this is 0.72% ionization. And remember, if it is 5 or below, you can ignore x. So because 0.72 is way less than 5%, you can go ahead and ignore the x, which means that our calculation here is just fine. We don't need to do anything else with this. So 1.3 times 10 to the negative 3 is the value of x, and that is the value of the hydronium ion present in there, which then if you find the negative log of, you will calculate the pH. Just want to bring a few things here to your notice. Okay, so first of all, the percent ionization is very less. Okay, for this acid, it's a very small ionization going on, 0.72% ionization going on. However, the weak acid, okay, it's still quite a good acid. Okay, 2.89 is a nice pH. Okay, considering that towards the 7 pH level is when you have real weak acid. So this is not quite such a weak acid. It's a fairly good acid. And also looking at the concentration, 0.18 molar solution is very dilute solution. Okay, so which means that even weak acids are actually good acids. Okay, it's just that the ionization is so low that you can ignore the concentrations of some things, but otherwise, you know, they're fairly good acids. So anyhow, that's how you would do the calculation for pH. Let's look at another example for calculating the pH of a weak acid. Para-hydroxybenzoic acid is used to make certain dyes. What are the concentrations of this acid, of the hydronium ion, and of para-hydroxybenzoate in a 0.2 molar aqueous solution at 25 degrees Celsius? What is the pH of the solution and degree of ionization of the acid? The Ka is given to us, which is 2.6 times 10 to the negative 5. Now here are a few things that you need to note. The initial concentration is 0.2. The temperature is 25, which really for us is going to be completely irrelevant because we're not calculating the pHs at different temperatures. So even if it is given to you, just go ahead and ignore the fact. And then we are asked to calculate the pH and the degree of ionization. And the Ka is given to us. Okay, and so what we will do is set up our equation first. And para-hydroxybenzoic acid, and if you're not an organic chemist, you're probably thinking, what the heck is the structure? And so don't worry about that, okay? Just go ahead and write an equation for a generic equation, because if it doesn't tell you if it is diprotic, triprotic, or anything, then you don't have to worry about multiple ionizations. So which means you have only one ionization, and if you have one ionization, this is the best equation for it. So just use HA as a generic acid for any acid that is given to you that you don't know the structure of. Set up an ice table like this as we have before. So Ha plus water gives us hydronium ion and then the conjugate base. So set up your numbers. Initial concentration is 0.2 and 0 and 0 for hydronium ion and conjugate base, and then the minus X plus X. And at equilibrium, you have 0.2 minus X and then X and X for the two ions, okay, as the concentration. So now we're going to calculate for X, okay, which you have done before also. So here is our Ka equation. Here is our numbers, okay, with the from the ice table and the Ka. Now we're going to figure out if we really need to calculate for X, and one of the ways to do this is also by taking the value of the concentration divided by 2.6 times 10 to the negative 5, which is the Ka value, and see if the number comes out to be really huge. If it's a huge number, then you can ignore X, okay? So which means that if you ignore this one, then X becomes approximately 2.00, okay? So again, remember, this has to be a really large number, more than 1000, okay, for you to be able to ignore X. The other way was to remember to ignore X and then figure out for X and then do the calculation, which I'll show you also in a minute, okay, if you want to do it that way. Okay, so then which means if you ignore the X, then this is your equation where Ka is X squared over 0.2, and so 5.2 times 10 to the negative 6 is X squared. Okay, and so that is of course by cross multiplication, and then you figure out the value of X, which is the square root of 5.2 times 10 to the negative 6, which is then the hydronium ion concentration. It's also the conjugate acid, but we need to find the pH. So then you find the pH of the solution, which is 2.64. If you did not understand this part about the X, you can also use this X value over here. So this X, 2.3 times 10 to the negative 3, divided by 2.6 times 10 to the negative 5 will tell you what the percent ionization is, okay, and you'll find out it's very, very low, so you can actually ignore the X value, okay. So that is the pH that is of this solution, okay. Let's look at a different kind of problem for this one. It's calculating Ka. Instead of calculating pH, we'll be calculating Ka and percent ionization in this one. So the question is, sore throat medications sometimes contain the weak acid phenol. A 0.1 molar solution of phenol has a pH of 5.43 at 25 degrees Celsius. So the question is, what is the acid ionization constant, which is Ka for phenol, and then what is the degree of ionization for this? So you set up your table as you did before. So here you have the phenol, and again, if you don't know the structure of phenol, it doesn't really matter. You know that it is going to be a monoprotic acid, and so here is the ionization concentrations initial, which is 0. At the change, it's plus X and then minus X for the acid. Equilibrium, again 0.1 minus X and then X and X for hydronium ion and the conjugate base. So then what we need to find out is the hydronium ion concentration, because we know the pH this time. This time we don't know the Ka, okay, because we are calculating for Ka, which means we need to know the hydronium ion concentration. So if pH is 5.43, then hydronium ion concentration is inverse log of 5.43, which is 3.7 times 10 to the negative 6. So which means that the X value is 3.7 times 10 to the negative 6. All right, this value over here, that's what pH tells us. So which means that the concentration of the phenol in the original solution is 0.10 minus X, and then remember X is 3.7 times 10 to the negative 6, which if you think about is 0.000, like 5 zeros. So X is really going to be small, which means that we're going to keep the concentration of phenol as 0.1. Okay, that is our concentration. So let's go on to the next slide where the problem continues and we'll see the new concentrations. So here is the concentration now. Remember, the ionization was so low that the original concentration 0.1 remains that, and the hydronium ion concentration and conjugate base concentration is this. So now we can calculate for Ka because this is how we set up for Ka. Okay, and so it's a very easy calculation now. Once you have this, you have the Ka value. Once you have the Ka value, then you can go ahead and calculate the degree of ionization from the original concentration. Okay, and so the degree of ionization is 3.7 times 10 to the negative 6 divided by the original concentration. Now for the degree of ionization here, you just needed to know the inverse log of the pH. Okay, you didn't really need the Ka for that, but this is part of our problem, so we'll just calculate that anyway. And so the degree of ionization is this much, okay, 3.7 times 10 to the negative 5, okay, that is the degree of ionization. So that's how you would set up the calculation. Again, they're fairly easy to do in the sense that either you're calculating for the pH or you're calculating for the Ka, okay. Oh, finally, the percent ionization, okay, that's this. All right, and then calculating the pH for weak bases. Weak bases are the same as the acids in the sense that, you know, they are also in equilibrium. Now, weak bases are going to have Kb instead of Ka, all right? And so they have hydroxide ion concentration on the top. So when you're looking for calculating the pH, you should be given the Kb. Even if you're given the Ka, you have to still figure out the Kb by using Kw. All right, so one way or another, you need to get to Kb, not Ka, because Ka is for acids, Kb is for bases. So solving for X again will give us the hydroxide ion concentration. Again, remember, not the hydronium ion concentration, okay, because we're talking about bases. So examples of some weak bases, okay, are ammonium ion, and anything that is related to ammonia, like this one, for example, this one will give us hydroxide ions. Again, just like I said for you for the weak acids, don't panic so much about what the weak acid is and what the structure is, because at this time you're not familiar with organic chemistry so much, so sometimes it's not uh, all that easy for us to write down the structure. So here also, I just need you to understand that if you have an ammonium ion somewhere, if you have ammonia somewhere, you're going to have a weak base. Similarly here also, okay, you have something similar to ammonia. So this is going to be a weak base, and that is enough. So here are some KBs for weak bases. And look at all of this, NH2, NH2, NH3. Here is again nitrogen. Okay, so wherever you have nitrogens in any structure, that's going to give you a weak base, and then the KBs are given over here. Remember, Ka times Kb is equal to Kw, and Kw is 1 times 10 to the negative 14. Okay, so that's how you can calculate Kb if Kb is not given to you and Ka is given to you. So keep that in mind. So let's do a calculation for Kb, and this is using pH to calculate Kb. pH is for acids and Kb is for bases. So you can see there is going to be slight difference in the calculation. So the question is, determine the Kb of a weak base if a 0.5 molar solution of the base has a pH of 9.59, again at 25 degrees Celsius, which is useless information, 25 degrees Celsius for us for right now. So here is how you would start solving the problem. First of all, since you are given the pH, you should figure out the pOH, okay, of this, because we're going to use the pOH to figure out the concentration of the hydroxide ion, okay. There is another way you can do this, but this is the easier way, okay, to do this. So pOH would be then 14 minus 9.49, which is 4.41. So then to figure out the hydroxide ion concentration, you take the inverse log of 4.41. Remember, you're calculating Kb. Okay, so if you're calculating Kb of the acid, you need to know the hydroxide ion concentration, which remember is the X and the X after hydrolysis, okay, or after ionization. So here's your equation setup, okay, which is the base, and it doesn't matter what base it is, it's a random base that gives you one hydroxide ion. The initial concentration is 0.05. The change now is going to be this concentration that you just calculated for the hydroxide, and so that is going to be the conjugate acid, and 3.89 is also the change that you would have for the hydroxide ion concentration, and that is because the pH was given to us, okay. And so at equilibrium you would have 3.89 times 10 to the negative 5 molar concentration for the conjugate acid, and 3.89 times 10 to the negative 5 for the hydroxide ion concentration. The concentration for the original base remains the same. Okay, so it was 0.5. So that remains the same over here because the concentration of the hydronium ion is so small, again 10 to the negative 5, that it doesn't really matter. Okay, so you don't have to subtract that. And so here is our formula for calculating Kb, which is the conjugate acid times the hydroxide divided by the base concentration. So this is how you would set it up. This is square. It looks 2, but it is actually squared. And that gives us 3.0 times 10 to the negative 9. That's how you would calculate Kb if pH was given to you. So just one additional calculation here. If you were being asked to calculate Ka, you would forego this one and start right from here, okay, by calculating the hydronium ion concentration. Slight difference. Polyprotic acids. Now, polyprotic acids are slightly different because they give you more than one ionization. So, for example, sulfuric acid, sulfurous acid, carbonic, and all of those, they will have more than one ionization. So, sulfuric acid will ionize once to give hydrogen sulfate ion, and then the hydrogen sulfate ion will ionize to give you sulfate ion. Usually, the first ionization is complete. The second one and the third one are not complete. Okay, so they will have ionization constants as in A1, A2, and so on and so forth. So when you calculate the pHs, okay, of such acids, you have to calculate the ionizations for all the protons and then add all the concentration and then calculate the pH. Okay, so you will find out the concentration of the first proton and the second one, and then add those two and then get the pH. So we'll do some example in the next slide. Okay, so here are some pKa's for the polyprotic, not pKa's, the Ka's for polyprotic acids. And so sulfuric acid, Ka1, is very large because you have a complete ionization for one proton. For the second proton, it's 1.3 times 10 to the negative 2, which is still fairly good, okay, for a second ionization. Look at all the other ones over here. The second ionization is really small, which means that even the one ionization is very hard, okay, for it to do. We're getting into really weak acids by the time we're looking at oxalic acids and sulfurous acids. Sulfuric acid is very strong, okay, so that's why the Ka1 is very good for it, and the second one is fairly good. But all the other acids in here, if you look at the Ka for these, the first one, and they're fairly small, and so therefore not very good ionization. Okay, for phosphoric acid you will have 3 Ka values because it's a triprotic acid. So if you're trying to calculate the pH, you will have 3 calculations to do. For calculating for diprotic acid, you have 2 calculations to do, one for the first ionization and then the second for the second ionization. So let's try it out. So let's do a calculation for a polyprotic acid and pH. So tartaric acid is a diprotic acid used in food products, what is the pH of a 0.1 molar solution, and then what is the concentration of the tartrate ion in the same solution. So which means we have to take it all the way. If you look at the tartaric acid over here, you have 2 protons, and here there are no protons, which means that we're talking about both of them being ionized. So we have to take it all the way to 2 ionizations. Ka1 and Ka2 are given to us because again you have 2 protons to ionize, so you need the Ka values for both of them. So let's go ahead and get started. Again, you start with your simple ice table. Okay, so the first ionization is going on here, and you're starting with 0.1 molar solution, and then for the hydronium ion you only have 0 concentrations in the beginning, and then at the end you will have XX. Okay, so similarly as you've done before, you will do it again. All right, so here is the Ka1 calculation, and here is your setup for the first one. Okay, now in this case you have to be careful. All right, you cannot ignore X in this case. So when you set up this final Ka1 equation, don't ignore X, because if you ignore X, you're trying to say that this polyprotic is behaving like a monoprotic acid. So you cannot ignore X. Okay, you have to carry on for X for the next ionization. All right, so do not ignore X, which means if you don't ignore X, you got to use quadratic equations. Sorry. So quadratic equation, this was cross multiplication from the previous slide. And once you do that, keep setting it up, keep setting it up, keep setting it up. Okay, so that takes a little time. It's not hard, it's just tedious. Okay, because if you remember from your math, yeah, quadratic equations are just little time consuming. So once you've done the multiplications and you've opened up the brackets over here, you get this quadratic equation, and then here is your A, B, and C values, and this is your quadratic equation. Okay, and usually I give this to you on the exam, so you don't have to think about memorizing it, although you should have it memorized from your math. Okay, however, I will give this to you. So once you have your A, B's, and C's, you can go ahead and set that up and do this beautiful, wonderful calculation. Now, don't forget to carry over the charges, okay, that you have. So for example, for the 9.2 over here, which is the value of C, you have to carry over the negative charge. If you don't carry over the negative charge, your calculations will not be correct. Here also you carry over the charge, which is positive, so it didn't really matter, okay? And here it started with negative here to begin with. Okay, so make sure you keep your charges straight. Okay, and then you will be able to do this calculation correctly. Okay, so once your X values are set, then you can calculate X, and X turn out to be these two values over here. Since this is plus and minus, you will always get two values for X, and then you have to decide which is the correct one. And you know that X cannot be a negative value, so this is going to be then your value for X. Remember what X is. X is the hydronium ion concentration. Okay, so which means that at the end of first ionization, your hydronium ion is 9.1 times 10 to the negative 3. The conjugate base is 9.1 times 10 to the negative 3. And the concentration of the acid, okay, is also given to you, which was what you started with. Okay, all right. Now we're going to go ahead and calculate the second concentration of the hydronium ion using these numbers, because this is now going to be our starting point. This is the conjugate base. This has the second proton, so this is the one that is going to undergo the second ionization. Here's our beautiful table, and so 0.0091 minus X, and then plus X over here. For these are your concentrations. Now remember, you already had 0.0091 molar concentration of hydronium ion already present in the solution. Okay, so now you're going to add more to it. So that is why this is already there. Okay, these numbers are already there. So anyhow, once your table is set up, again, you will go ahead and set up your Ka values. And in this case, you can start to ignore X. Okay, because in the first one you can't, because it's the diprotic acid, but in the diprotic acid, the second one you can, because in general, the second ionization is going to be very weak. We know that already also, and then we don't need to continue on to the third one, So honestly, it doesn't matter. Okay, so now you can ignore your x, and yes, that makes our life so much easier. So then this is the value of x after doing all the calculations. Okay, remember you're ignoring the minus x and you're ignoring the plus x over here. So the only x that's remaining is this x, okay, over here. So it makes life a lot easier for us. And so then you calculate the final pH, okay, using this x value. By the way, this little calculation shown over here is that once you calculate x, you can divide that by the original concentration, which was 0.0091, and figure out the percent ionization, which, if you remember, has to be less than 5% to be meaningful, to be ignored. Okay, so this is definitely less than 5%, so you can completely ignore x in this case. So then you calculate the final pH, and these are your concentrations that you have for all the three ions in there. This is the tartrate ion, okay, which is then 4.3 times 10 to the negative 5, which is what you calculated here. The concentration of the monotartrate one, okay, which had only one ionization going on, that is going to be this, which is 0.0091. That is what you calculated. And then the hydronium ion concentration is 9.1 times 10 to the negative 3, which if you add 4.3 times 10 to the negative 5 to this, it's almost meaningless, okay, because that's 0.00005, okay, 4. So that's really, it's really very, very less amount. So it doesn't make even a dent in 9.1, okay. And if you want to, you can. You should add this one up and this value up. Okay, and then you're going to use this value for the calculation of pH. If you want to, you can add those two up. Okay, no problems. And you will see that your pH really doesn't change a whole lot. Okay, and so it will be 2.04 once you've calculated the negative log, okay, of this value over here. So that's how you would do for polyprotic acids. So it's just a little bit of a lengthy calculation, not a hard calculation, because you can't ignore X in the first ionization. So you have to go through the quadratic equation. There is no way out. So your key concepts from this little portion is to be able to calculate the pH and the pOH of weak acids and bases. Of course, you'll be given the Kas and the Kbs. You should also be able to calculate Ka and Kb of weak acid and bases, which means that you might be given the pH or the pOH. Okay, so look at what is given to you, and that's how you will start your calculation. And then, of course, the calculation of diprotic acid. The examples that I've given you in this presentation, those are the key examples. Those are the only type of variations you might have in calculating pHs and Kas and all that.